Hi everyone! Today I will talk about our recent work, SITTA, Single Image Texture Translation for Data Augmentation, a general solution to examine how SITTA and related image translation methods can provide a basis for data-efficient augmentation engineering approach to model training. In the wild, it's very hard and impractical to connect balanced datasets for training recognition models. For example, connecting healthy leaves is easy, while collecting sick leaves could be comparatively very difficult and expensive. Our goal is to study the potential use of image synthesis methods for recognition tasks. Here are two key limitations. First, the validity of synthetic data for target labels. Second, the running time. To solve this problem, we select data augmentation strategy as our primary direction. We provide a simplified illustration of the data augmentation landscape in the figure. Data augmentation plays a critical role in various image recognition tasks. On the one hand, basic image manipulation methods have been widely used as effective pre-processing tools, with examples including flipping, rotation, jittering, grayscale, and Gaussian blur. Several works explore effective combined choices of basic image manipulations. Luke searches for an optimal augmentation strategy among a large pool of candidates based on a specific dataset or tasks. Mix-up interpolates two training inputs in feature and label space simultaneously. Cut-mix uses a copy-paste strategy and mixes the labels in proportion to the number of pixels contributed by each input image to the final composition. MoX exchange the moments of the learned features of one training image by those of another and also interpolates the target labels. However, few of them explicitly augment data with natural outputs that could be used to solve real problems. In this paper, we propose SITTA that generates new data semantically while domain-specific texture translation. We start our design from two parts. Data augmentation. It enables one to translate images by learning the mapping between a source domain and a target domain. And second is single image texture translation. It translates texture to augment images based on a single input of source texture. Our methods enables one to translate images by learning the mapping between a source domain and a target domain. First, it's leading to consistently improved image recognition performance. Second, it is allowing for fast training and testing. In this figure, we could show the Sita flow, the single image texture translation for data augmentation flow. We first obtain textures from sick leaf and content from healthy leaf. Then we feed them into Sita model to generate augmented data. We set the corresponding label as sick. In this figure, we illustrate an example of generated bubble milk images by translating the texture of bubble milk to milk images. We visualize the image distribution using t-SNE. We connect 100 natural milk images and 100 natural bubble milk images from the web, shown on the left. On the right, we can see that Sita bubble milk images align well with the original bubble milk images, which hints the efficacy of Sita for semantic data augmentation. Sita aims to augment images that align with the target texture domain and could be used as extra training data for various recognition tasks. Assume we have plenty of source domain images set A but a few target domain images set B. The only difference between set A and set B is that they can obtain different textures. Our goal is to synthesize extra B data by replacing textures of set A with the new textures from set B. We call the augmented dataset as augset_B. This figure shows a brief sketch of our framework. To achieve efficient model design, we emphasize three critical components: input augmentation, structural information reinjection, texture latent regression. The first is input augmentation. We propose to directly augment input by horizontal flip, center crop, and random crop. We found such input augmentation could effectively guarantee the diversity of image scales for fast and efficient training. Second is structural information reinjection. To better preserve the structural information and optimize training, we apply positional norm to extract intermediate normalization constants, mean, mu, and standard deviation, sigma, as structural features, beta and gamma, and reinject them into the later layers of decoder to transfer structural information. And third is texture latent regression. To achieve better representation disentanglement for texture and content, we use the latent regression loss, identical loss, to encourage the invertible mapping between the latent texture vectors and the corresponding outputs, and enforce the reconstruction based on the latent texture vectors. Sita is based on GAN framework. The loss function is composed of 5 parts: adversarial loss, latent regression loss, content matrix reconstruction loss, textual vector KL divergency loss, and the perceptual loss. During training, we have inputs IA and IB, extracted texture vectors TA and TB, content matrix CA and CB, corresponding normalization constants beta A and beta B, and gamma A and gamma B, as well as outputs I' A and I' B. Adversarial loss is GAN standard loss function for matching the distribution of translated image to the target domain. We have 2 discriminators for distinguishing between real and generated image for A and B domains separately. Identical loss makes sure that decoder is able to reconstruct it based on extracted content matrix and texture latent vector. LREC is based on cycle consistency loss that optimizes the training for this under-constrained problem and regularizes the translated image to preserve semantic structure of the input image. To better preserve the structural information, we use perceptual loss based on VGG lighting between the generated outputs and the original inputs. We use KL divergence loss to minimize the distribution variance between extracted texture vectors from the target image and generated image. To sum these loss functions up, we display our final objective functions, where lambda are weights assigned for each loss, respectively. Now, we will talk about the experimental setup. During training, we use ADAM with 0.0005 learning rate. Beta 1 equals 0.5 and beta 2 equals 0.999. We augment the inputs and resize them to 288 multiplied 288. Empirically, we find the model starts to converge after 600 iterations and becomes stable after 800 iterations for every input pair. We use widely used datasets as well as images connected from internet. For low-level evaluation of augmented data, we randomly select 32 images and run the experiments for 3 times with a single source and target image. We report the average score in the table. We could notice that Sita could achieve comparatively better scores. We show some of the corresponding qualitative comparison results. We could observe that Sita enables clear and reasonable outputs. Given that Sita aims to learn a texture mapping between source image and target image but preserve general content, we utilize positional norm to extract structural information and reinject them into intermediate layers of decoder. To evaluate the impact of this operation, we compare our results with or without positional norm reinjection. In the figure, we show comparisons of similar structural modes and different structural modes that 2 inputs share similar or different structures. It could be noticed that positional norm reinjection effectively regularizes the model to preserve its original content and avoid obvious unclear regions, color distortion, and weird spots for a reasonable output. Sita is a lightweight yet efficient network. Here we show the comparison of average training and testing time per iteration in an epoch using the same single GPU without acceleration in the table. We could notice that Sita achieves fastest testing with an obvious edge. Though our style could be trained very fast, it cannot achieve texture translation very well, while Sita shows its superior advantage considering training iterations, training time, as well as model performance. In this section, we use Sita to translate the texture from the few sick leaves to the healthy leaves to obtain more sick data. We use Plant Pathology 2020 dataset that provides data covering a number of categories of foliar disease in apple trees. We select healthy and multi-disease classes as healthy and sick and randomly flip the dataset for training and testing. The training set consists of 416 healthy images and 1 sick image. The test set consists of 100 healthy images and 81 sick images. On the whole, we have 3 types of training data. We refer to the single sick image as baseline. To solve the imbalanced data problem, we repeat the single sick image to match the healthy data count and refer to this operation as repeat. To validate the augmented dataset, we use t-SNE to visualize the distribution of repeat, targeted test set, and Sita. In the figure, we see that the augmented data shares a similar t-SNE distribution with targeted test set. In the table, we show the comparison of various augmentation strategies based on ResNet 18, consistent with previous results. Sita improves the baselines with a large margin and is even highly competitive with state-of-the-art methods mix-up, cut-mix, and MoX. Also, since Sita generates new data that could be easily used with any augmentation methods, it could be observed that Sita is compatible with other augmentation methods and consistently help boost the model performance with obvious edge. We display the results in the figure. We could observe that Sita significantly outperforms other methods for data augmentation. Here we display the Sita augmented examples. Furthermore, Sita could be used in other tasks. Here we try Sita for few-shot image classification on Oxford 102 flowers. It could be obvious noticed that Sita is able to improve the classification on 102 classes without any additional fine-tuning on real images. The results are very inspiring and show the consistent edge regarding different model architectures. Similarly, we observe the consistent and competitive improvement of Sita on Caltech UCSD BIRDS 200, which sheds light on the feasibility of Sita for future learning tasks. Following previous long-tailed classification settings, we compare the iNaturalist birds classification results and display them in the table. It could be observed that augmented birds are able to help improve the classification performance, which is consistent with the results of leaf classification. Beyond mimicry or camouflage in natural worlds provides some real examples for texture swamping that creatures mix the texture of their body similar to the environments to avoid danger or hunt food. For instance, we show the case of mantis or orchid. To prey for the insects, mantis will adaptively change their texture similar to the orchids. In the figure, we give an illustration and find Sita could translate the orchid's texture to the mantis and obtain reasonable and natural outputs that looks very close to the real example. In summary, we introduce a new lightweight single image texture translation method for data augmentation, Sita, that translates textures from a single image to another. Second, we explore the use of Sita for augmenting data towards the target texture domain. As an example, we translate texture from rare diseased leaves to abundant healthy leaves to augment training data and improves image classification results in the plant pathology challenge datasets. Third, we dig deeper into the use of Sita for augmenting data and demonstrate its effectiveness in several image recognition tasks. For example, improving the performance of ResNet 18 by 1.4 for 5 shots classification on CUP 200 2011, which sheds light on the potential directions of image synthesis for data augmentation in the wild. Here we provide a demo to further showcase how Sita works. For more details, please feel free to check our project page. Thank you.